Today I will be showing you how our design space search module can be used to optimize the macrogeometry of a single gear set. Design space search works on both cylindrical and bevel gears and can also be used on planetary gear sets. You specify which macrogeometry parameters you want to vary, and MASTA will create a design for every combination of the input values.
This allows you to easily compare rating results and geometries for lots of different designs. Design space search isn't an automatic solver. Instead of giving a single answer, it gives lots of possible candidates and allows you to choose the most appropriate candidate. It can be used by experienced engineers to help design a gearbox, justify their design decisions to others, and check the robustness of the design to manufacturing variability. So if I open the planetary gear set, so it can work on a single load case or a duty cycle under the Design Space Search tab. I'm going to put together a quick example to show you the basics of how Design Space Search works. First, you need to specify your strategy that includes parameters you want to vary. So you do that by clicking the Design Space Search strategy button. So for this example, I'll create a new strategy, but we do provide default strategies. So I'll add normal pressure angle, just as an example. So the number of candidates created is specified by the number of steps property. MASTA will create n+1 candidate designs with different pressure angles. With a value of 1, there will be 2 candidates created. If I set it to 9, then there will be 10 created. And similarly, if I specify 99, there will be 100 designs created. I'll just quickly add a couple of outputs. I specify a minimum value of 1. That will be used when filtering designs and also when throwing away designs that have very good values. I'm going to specify a symmetric deviation from the original design absolute values. So with these values, MASTA will create 100 candidate designs with a pressure angle ranging from 10 degrees less than the original design to 10 degrees above. If I click the Create button, you can see that we have the candidate design chart selected. This shows the original candidate as a star and any rating or gear geometry parameter on the X, Y, and Z axes. So I can click the X-axis property and choose the normal pressure angle. As an input. So here you can see that as the normal pressure angle increases, the safety factor contact increases as well. You can add multiple charts. So if I add another chart, I can change the chart type to bar and line. And this will by default give you a bar for each output selected. So here you can see that we have a range for safety factor bending from 1.4 to around 2, and it lists the original candidate as the orange bar. If you select a candidate using this slider, you can see the selected candidate is highlighted in red. The blue colours denote the number of candidates around that safety factor value. So you can see that most of the safety factor contact is quite high, around 1.1. With a candidate selected, you can see in the bottom left the candidate design drawing. At the moment this is showing the mesh, but you have various options to show different gear geometry parameters. If you slide the bar on the right, you can see the candidate moving and also the gear design drawing changing. You see that as I increase the normal pressure angle, the teeth become sharper. So here I've selected the candidate with the highest normal pressure angle. If I go back to the first chart, you can see that it is still selected. With a candidate selected, you can set the backdrop on the candidate design drawing tab and then compare that with other designs. So if I hold down Control and move the mouse over candidates, it's selecting them in turn, and again you can see the teeth become sharper with their pressure angle changing. So when you have a candidate selected, you'll have the option to see the geometry and rating report for these candidates.
Just click on the screen control. Yeah.
It looks like some of you have got problems with the screen sharing. We'll just try and find a solution. This one.
This one. Okay, apparently the webinar is available on our website. I'll try to select the screen area.
Okay, sorry about that. So if I go back to the candidate designs chart tab, I can show you how to filter design. If you click the filter button, you'll get the option to filter candidates based on the values selected in the outputs. So if I select a filter of 1.1 on contact, click OK, you can see that got rid of all the candidates with a safety factor contact less than 1.1. You can click filter again and change the values. So if I put 1, you'll get a few more candidates back. Okay, to make this example a bit more realistic, I'll add another input. This time I'll add the helix angle. An absolute range of 0 to 10 degrees. Set the number of steps on both to 9. I'll change the normal pressure angle distribution to 5% either way because 10% is quite high. So MASTA will now create a new design for every combination of the inputs. For example, there will be 10 designs with a helix angle of 0, but they'll all have a different pressure angle. So in total there will be 10 times 10 designs, so we should have 100 candidates created. So I'll add a default chart. This will appear in the list of charts. So I'll keep the bending and contact safety factors on the X and Y axes and add just total gear set reliability. As you can see here, MASTA has calculated that the total number of candidates to be evaluated is 100. So it's managed to create 71 feasible candidates out of the 100. So in this chart you can see safety factor bending against safety factor contact. And you can see that there seems to be some groups of designs that look like they're related to each other. So that group and that group going down there all seem to be related. So design space search allows you to investigate the relationships between these groups. So if you select a group of points, you can then hold down Shift and select some more points. And then go to the valid candidate designs table. In here, if you select candidates selected in chart, it will only display the candidates here that were selected in the scatter chart. And you can see that the relationship between these candidates is that they've all got a helix angle of 0. But if you wanted to order these candidates, you can order by bending, then contact. You want. So we'll make the strategy a bit more complicated still. And add the number of teeth. And I'll keep this as a symmetric deviation from the original design. So I'm going to, you can see here it wants to create 35,000 candidates, which will take a long time. So I'm going to fix the property on the annulus and the planets and only change the number of teeth on the sun. Any property that has fixed this property check won't be modified by MASTA. So now it's only going to create 500 candidates. So here we have our candidates created. You can see out of a total of 500 candidates, only 229 were feasible. The reasons for invalid designs tab shows why various candidates were invalid. We've added some properties that can help you keep a valid design while varying the macrogeometry. So instead of normal pressure angle, I'll choose normal pressure angle, maintain transverse profile. This keeps the transverse profile constant. It maintains the two proportions, and that helps keep designs valid. I put the same values as for normal pressure angle. And then we have a similar property for helix angle. And for number of teeth, we have a property, number of teeth maintaining ratio, calculating normal module. And that will change the number of teeth on the meshing gears to keep the ratio as constant as possible, and it will also change the normal module to keep a valid design. So click OK to that, and then fix the properties on the parameter and annulus again. See, we're going to attempt to create 500 candidates. So here you can see we've got 466 feasible candidates instead of the 229 there was before. So, as another chart, to show that the ratio has stayed relatively constant, even though we're changing the number of teeth on the sun. So here you can see, as we've changed the number of teeth on the sun, the number of teeth on the planet has also been modified, and the ratio has stayed relatively constant to well within 1%. So now, if we go back to the Certifacts chart, we can do a dominant candidate search. That will remove candidates that for every output are worse than another candidate. We can choose a design that we think looks interesting. That one has got a relatively high Certifacts constant. You can check the values in the report, and when you're happy with it, you can add it, and it appears on the left to to be analysed further in system deflection or another design space search. Okay, so the next example, I'll show you how to optimise the macrogeometry of a gear set for efficiency. This is based on an article in Gear Technology magazine in 2007 by Hon, I think. So it's an example of gear set optimisation using design space search. We'll try to reproduce the results from that article. So on our examples menu, we have an MSRG type C example. The article discussed several macrogeometry parameters that affect the power loss. One of the parameters was pressure angle. So we can use design space search to try and reproduce the results of in that article. So if I add pressure angle as an input, with a range of 14 to 26 degrees. And chart, put the chart of normal pressure angle against energy loss. This very quickly analyses the 100 candidates. And you can see from this chart that the energy loss reduces with increasing pressure angle. And this chart looks almost exactly the same as the chart in the article. The low loss gears article lists the main macrogeometry parameters that affect efficiency. So we've included them in the default strategy. So if I click the strategy button, see we've got a default strategy, low loss gears. If I duplicate that, you can then edit the values. So I'll reduce the number of steps from 4 to 3 just to reduce the amount of time it takes to run the analysis. And I'll also reduce the normal pressure angle. So that was adding 20 on to the existing design. Try change that to 10, and that will give a maximum pressure angle of 30, which I think is probably high enough. You can add a default chart, bending and contact against mesh efficiency. And I will fix the wheel number of teeth, which, as you saw before, will be varied because we're maintaining the ratio when setting the pinion number of teeth. That took a while to complete because there were so many candidates to evaluate. You can see the output looks quite good. Quite a few valid candidates. I know from experience that there's a problem with the original design, I think, in this, that the hunting factor is quite high. This shows the chart of the hunting tooth factor against the mesh efficiency. Really, you probably wouldn't be interested in a gear pair that had this sort of hunting tooth factor. So if you select the ones you are interested in, you can then go to your safety factor chart and see the selected good designs there. If you now do a dominant candidate search, you can see there's maybe four examples that have got a good hunting factor and a good safety factor concept. So you would choose one of those, check you're happy with it, and then add it into MASTA for further analysis. I can see people are still having problems doing this on their screens. I think it will be available on the website, and if anybody's got any questions after watching the video, they could give us a phone call or an email, and we'll try to address any questions. So for the final example, we'll look at sensitivity analysis. So design space search can be used to test how sensitive a gear set design is to manufacturing variability. I open the Scooter Gearbox. In order to set this up, you need to know a bit about gear geometry. So one example of manufacturing variability is tooth thickness. And MASTA gives a tolerance to tooth thickness. So that reflects the manufacturing variability. It's important that at the minimum thickness, the bending safety factors are still okay, and at the maximum thickness, the backlash isn't negative. So to check this with design space search, we need to set up the design so that we can specify the average mean metal, which is here. Now, we've got a gear fit system of DIN specified. That constrains the system so that there's only 1 degree of freedom. To set the thickness on both gears, we need to set the gear fit system to none. So here we can also specify a tolerance of 0, and that forces the maximum and minimum metal to be the same. So when we vary the average mean metal, it's varying all of them. So if I set upper allowance to be calculated, there are 2 variables that can be set now, where you can set average mean metal. So design space search will set these anyway, but I'm going to specify them just to lock down the design. It won't make any actual difference in design space search because it's just a bit nicer. So now, if we go to design space search, we can add a new strategy. So we want to vary the mean metal is on the finished toothpick specification. There I can select the original metal. And we'll give that a symmetric deviation from the original design, absolute. And as the tolerance was 40 microns, I think I'll specify a symmetric deviation of 0.02 either side of the original design. So there are other properties that can be affected by manufacturing tolerances. One is the basic reactive addendum factor. Now, if there's a property that you're not sure where it is, like I'm not sure where the addendum factor is, you can search in the box at the top, and it just makes it a lot easier. So for the addendum factor, I think a deviation of 1% probably would be realistic for a manufacturing variability. So the tip diameter on gears can also be affected by manufacturing tolerances. So I'll give that a variation of 0.1. So I'll set the number of steps to 2 on all of these. That will check the extremes of the inputs and also the middle value. You could check more, but it would take longer to analyse. Now, the output, the things you might care about would be you're varying the thickness, so you'd want the normal backlash to be positive. So you'd want your minimum normal backlash to be greater than 0, at least, or you might have an inbuilt company tolerance. That value. I'm going to click exclude from dominant candidate search because bigger value of backlash isn't necessarily better than the minimum value. I'm going to also add the bending and contact safety factors. Give those the minimum value of 1. The tip clearance, I think that could also be affected by the tip diameter. So you would want your tip clearance to be positive. And I'll exclude that from the dominant candidate search as well. Now, in the results, you really want to check that your safety factors are within the allowable range and your minimum backlash is greater than 0. So if you click filter, just as a quick check, you can check all of those things are true for within the manufacturing range by checking that the number of candidates after filtering is the same as the number of candidates before filtering. Okay, thank you for listening. I'm sorry about the display problems. If you'd like to listen again, the webinar will be available on our website in a couple of days. And if you've got any questions, send us an email or give us a phone call and we'll try to answer them. The next webinar will be on MVH and MASTA, presented by Dr. Owen Harris on 26th of April. And I promise you that time the display problems will be fixed. Visit our website to book.